All right. Does anybody have any questions about the homework that was due today? Yeah.
I found that the energies weren't equal.
Did everybody find that the energies weren't equal?
Yeah.
Okay, good. So basically charge sharing, when charge sharing occurs, charge is conserved, but energy is not conserved. And that's because it requires energy to move the charges. So some of the energy that's stored in the capacitors is lost when the charges get redistributed to the parallel capacitance. So if you calculated them to be equal, then you would have done something wrong. When you do the math, they will not wind up being the same. Any questions about anything else on the homework? Pretty easy. All right. Well, did everybody turn in their homework so far? All right. Well, okay. So last time I kind of glossed over. Let's see. What did I gloss over? I glossed over the idea of RC circuits and how when we actually charge a capacitor or discharge a capacitor, we're going to be charging it or discharging it through a resistor, right? In real life, capacitors charge and discharge based on this exponential equation, okay? And today I'm basically going to derive that equation for you guys, and then we'll do some examples. But first, I have to derive some other things before we get to this. Although it's all related to stuff that you already know. Let me just pull this out of here. So far we talked about the equation CV equals Q, right? The capacitance times the voltage across the capacitor. That basically gives me the charge stored on the capacitor, right? So let me go back to the camera. All right. So far we know that C times V equals Q, right? Do you guys remember, I may or may not have even talked about this in this class, but what current is, right? Current, in general, like by definition, it is the rate of change of charge with respect to time. It's basically telling us how much charge flows per unit of time. So if you're looking at, like, let's say this is a wire. And I've got some charges in here, some negative charges flowing through like some cross section of this wire. The current through that wire would be defined by basically how much charge flows per time. That's what current is by definition, okay? So if I come back over to this equation, which I know this governs the operation and charge of capacitors, what I can do is I can take the derivative of both sides of this equation with respect to time, where voltage across the capacitor and the charge stored on the capacitor are both functions of time. So I'm going to rewrite this as C times V of t is equal to Q of t, okay? So it's the same equation, it's just saying my capacitance is fixed, right? Capacitance isn't going to change. That's a rating for your capacitor. It's a fixed number. The voltage across the capacitor is some variable. It can change with respect to time, and as a result, the charge stored can also change, okay? So if I take the derivative of both sides of this equation, I get that C dV of t dt is equal to dq of t dt. All right? Well, I just said that current is dq dt, right? So this is where I get my equation for the current through a capacitor, which we haven't talked about yet, but this is where that equation comes from. So if I replace this dq of t dt by I get that I of t is equal to C dV of t dt. and this is very, very important. You're gonna see this all throughout engineering. This is derived using a derivative, of course, but we're not going to be doing any like actual calculus in here. You're just going to need to know that this derivative of the voltage is plays a factor in what the current is flowing through my capacitor. Okay, so if I had to explain this in words, it basically says that the current flowing through a capacitor is equal to the capacitance multiplied by the rate of change of the voltage. Okay, and that means that if my voltage isn't changing, I have no current flowing. Okay, so if I just have a fixed voltage across my capacitor like I do in a DC circuit, no current will flow. Okay, so that brings me to another important point, and that is that capacitors act like an open for DC. Okay, so if I'm just looking at some DC circuit and all the voltages are fixed in the circuit, no current will be flowing through my capacitor, and the reason is that this term right here, this dV of TDT, is going to be 0, which means my current has to be 0, right? So just as a quick example, if I'm sitting here with 5 volts, a resistor, and a capacitor in a DC circuit, nothing's changing. After some period of time, when the capacitor's charged, let's just say 1K, 1 micro, my voltage across this capacitor will be 5 volts. But that means that my voltage here and my voltage here are both 5 volts, right? So I, in this case, would be 0. Both sides of my resistor are at the same potential, right? So you could either look at this as, you can look at this in two ways, right? My current I is equal to, let's call this Vin, and we'll call this Vc. Basically Vin minus Vc over 1K. But if Vin and Vc are equal, then my current is 0, right? But also, I know that the current through my capacitor is C times dV dt. And since my voltage isn't changing, this is 0. So in both of these cases, I get that I equals 0, basically. And so that's why capacitors act like an open for DC. Okay? That's going to be important. And so then as, voltages are changing in AC circuits, and any time that the voltage changes with respect to time, we get some current flow. And so that right there is going to be a part of what governs the operation of these RC circuits and how they charge. Okay? So what I first want to do is I want to derive the equation which tells us how a capacitor charges, and then we'll do some examples. We'll do them in SPICE, and then hopefully for the second half of the class I can derive the equation for how a capacitor discharges, which is very similar but slightly different. But before I move forward, does anybody have any questions about anything I did here? All right, cool. Let me go ahead and grab another piece of paper. This might be a couple page long derivation. It's nothing crazy. It's just getting it set up, and there's some algebra involved. All right. So let's say I've got a circuit with a voltage source connected to a switch. I've got a resistor here, and I've got a capacitor here. Bless you. And let's say that this voltage here is Vc, the capacitor voltage, and that it is initially 0. Okay. Well, initially there's no current flowing in the circuit, right? And if there's no current flowing in the circuit, then the capacitor can't charge. And the reason there's no current flowing is because there's an open right here when this switch is open. Okay, so let's say at some time I'm going to close this capacitor. Or sorry, I'm going to close this switch. And now I've got a complete circuit here where current will start flowing and start charging the capacitor. Okay, and the reason why the capacitor is charging, again, I just said that the current that flows in a capacitor is equal to C times dV dt, right? Well, if I have some initial condition here where this is 0 volts and this voltage is going to be Vs, then my initial current is going to be Vs minus 0 over R, right? Bless you. Everybody sees that? My current flowing is going to be Vs minus 0 over R, okay? So that's going to be my current right when the switch first closes. And that's going to be non-zero. And so then, since this current is non-zero, that means that my change in voltage across the capacitor with respect to time is non-zero, right? If this term over here is non-zero, then that means, and this C is constant obviously, then that means that this term over here has to also be non-zero, which means that my voltage across my capacitor is changing with respect to time. Thus, it's charging, right? Okay. So now, what I'm going to do is I'm going to do a KVL around this loop. I'm going to do a KVL around this loop. Just so you guys know, again, I'm deriving this equation. You're not going to need to know how to derive it. It's good to know how to derive it, but all you're going to need to know is how to use the equation. So if the derivation doesn't make perfect sense to you, that's okay. Obviously, feel free to ask questions if you have them. But the first step is to do a KVL around this loop right here. So if I'm doing a KVL, I'm going to start here and I'm going to go this way. So I'm going to say Vs, right, minus I times R, my drop across this resistor, and then minus my drop across the capacitor, which is Vc, equals 0. So that's KVL. Everybody see that? Any questions about that KVL? I went up across the voltage source. I dropped some current, or I dropped, let me call this current I. I dropped by I times R across the resistor, and then I dropped by Vc across the capacitor. Okay? So now I have my, I know that charge, again, or sorry, current is equal to dq over dt, right? It's the rate of change of charge with respect to time. All right? So this is the first equation that I'm going to need. And then the second equation that I'm going to need is that C times V is equal to Q. All right? And the reason I need that equation is because what I need to know is the initial voltage across the capacitor in terms of Q. So Vc, right? I could rewrite Vc in that case as, if I divide both sides by C, it would basically be Q divided by C, right? So now what I'm going to do is I'm going to plug in dq dt for I, right? So I'm basically doing substitution. This is dq dt times R, and then I'm going to replace Vc with Q over C. And so now what I end up with is this differential equation, right? I've got Vs, which is my source voltage. I've got my rate of change. This is my current, but it's in terms of Q now. And then I've got my capacitor voltage, which is also going to be in terms of Q. And so once I get this equation written out, just like this, I can add these two negative terms over to the other side. So I can say Vs is equal to basically dq dt times R plus Q over C, right? And now what I want to do is I want to get dq dt by itself. Well, if I wanted to get dq dt by itself, I guess I could have just not subtracted the other term over. Yeah, question?
Why did your Q over C go to positive if it's still the same sign?
I added it to the other side.
Oh, you did. Okay, I see.
Yeah, but it's looking like this derivation doesn't actually want me to do that. Hold on. Yeah, so they want you to get dq dt by itself, basically. So let me just scrap this step. So if I'm going to get dq dt by itself, it would make more sense to just add this term over to the other side. So then I end up with Vs minus Q over C is equal to R times dq dt. And then I can divide by R on both sides. So I basically get 1 over R times Vs minus Q over C, and that's going to be equal to dq dt. Okay, so now I'm going to basically move this over here and keep going. And so now what I have to do, I don't know how familiar everyone is with differential equations, but I basically have to do what's called a separation of variables, where I get my dq on one side of the equation and I get my dt on the other side of the equation, so then I can integrate both sides and I can solve this equation. Those are called ordinary differential equations. How many of you guys taken 431? Okay, so for those of you who haven't, don't worry. Again, this is just a derivation, so you can see where the equation comes from. So what I'm going to do now is I'm going to do the separation of variables, which gets me to basically move the dt to the other side, so that I have the dt on one side and the dq on the other side. So I end up with 1 over r Vs minus q over c dt is going to be equal to dq. Okay? And now what I'm going to do is I'm going to pull a 1 over c out of this piece inside the parentheses. So if I pull a 1 over c out, I basically get 1 over r times c, but now I have to put in Vs times c, right, because I pulled a c out that wasn't there, minus q equal to dq. And now the last thing I'm going to do is I'm going to divide both sides by this piece in the parentheses. So I end up with 1 over r times c dt is going to be 1 over Vs times c minus q dq. Did I do something wrong? The c is supposed to be on the bottom. Did I do something? Did anybody see any problems here? So I pulled out a 1 over c from this Vs, but there was no c there, so I had to put a c in so that c over c would give me a 1. And then from this I pulled out a c, so now if I were to multiply that back in, that'd be q over c, right? Okay. The last thing that I have to do is I have to multiply both sides by -1. Basically, all these things seem kind of random, right? Like, why would you even pull out a 1 over c? But the reason is so that I can get it into a nice, neat form at the end, and you'll see. So if I multiply this side, I get minus 1 over rc dt, and then over here it's going to flip what's going on the bottom, basically. Okay, and so now I can integrate both sides. I'm going to integrate from time 0, which is when the switch closes, up to some time t, when I would want to check the voltage across the capacitor. Okay, and then I'm going to integrate from 0 charge, which is my initial charge across the capacitor, to some charge q at that time t. Okay, and so what I get when this entire term is just a constant. 1 over rc, r is going to be some resistance, and c is going to be some capacitance. Okay, so when I take that integral, all I get is negative t over rc. All right, and then on this side, I'm basically going to get, let's see, are you guys familiar with integrating like 1 over x? It gives you the log, or the natural log of x. So if I integrate this this equation here, I get basically the natural log of q minus Vs times c evaluated from 0 to Q, right? So this is not the equation. This is still ugly. But I am going to need to go on to another page to continue this derivation. Let me see if I could set that there and all right, yeah, cool. I'm just going to hold it for now. So you guys see that I'm going to drop that down. Evaluated from 0 to Q. All right, great. So now from here I would first evaluate it at Q, and then I would evaluate it at 0, right? So it's going to be minus T over RC is equal to the natural log of Q minus Vs times C minus the natural log of 0 minus Vs times C, right? And I don't know how familiar everyone is with log rules, but now what I can do is I can turn this into a quotient, because basically ln of A minus ln of B, that rule is that ln of A minus ln of B is equal to the ln of A over B, right? Okay. So negative T over RC is going to give me the natural log of Q minus Vs times C over 0 minus Vs times C, which is basically just negative Vs times C. Still ugly. I'm not done. We're getting there. Now what I can do is I can exponentiate both sides to get rid of the natural log, right? So that goes away. So now I'm left with e to the minus t over rc is equal to q minus vs times c over negative vs times c. All right. Now what I can do is I can multiply both sides by minus vs times c to get rid of this, right? So I have minus vs times c times e to the minus t over rc equal to q minus vs times c. And now I'm going to add this term to both sides, and that's going to go away. So I basically get vs times c minus vs times c e to the minus t over rc is equal to q. This q is the charge stored on my capacitor, okay? But in this class, I'm not going to be, I just wanted you guys to get used to that equation so that, literally for this purpose, so that I could do this derivation and it would be comfortable. We're going to be looking at voltages on the capacitors because you're not typically looking at charge stored. I might ask it again sometime in the future, but it's really not important. But if I want to get this in terms now of voltage, remember that voltage times, C times V is equal to Q. So if I wanted to get charge in terms of voltage, I can divide by C. And so I'll get V is equal to Q over C, right? So if I divide both sides of this by C, I can basically take the C out of both of these terms, right? And then this, Q over C, is my capacitor voltage at any given time, okay? So finally, I get to the equation that Vc of t, my Vc is going to be a function of t, that's my capacitor voltage, is equal to Vs, I'm going to factor a Vs out of both of these terms also, just to make it neater, 1 minus e to the minus t over Rc. That is my beautiful final equation. Okay, and that is for charging a cap. Okay, so I did a lot there. Again, the derivation isn't super important. What's important is the equation. So let's talk about the equation. This is telling me that if I have an RC circuit, let me draw an RC circuit, with some voltage Vs charging it, my voltage across the capacitor is going to change with respect to time by this function here, this exponential function. So if I plug in, let's say my switch closes at time t equals 0. That's typically when it's going to be closing in practice. It could be any time, but let's say it closes at time t equals 0. If I want to know what is the voltage across my capacitor at any time, I can plug in the source voltage, I can plug in R and C, and I can plug in a time. And I'm going to get the voltage across the capacitor at that time. Does that make sense to everybody? So all that ugly calculus and differential equations to get to this final equation. This final equation turns out to be very nice. It's a function of t, and then, you know, your source voltage is a constant. This is constant. RC is also constant. So it's really just a function of t. I mean, that's why it's written as a function of t, right? But it's kind of convenient that the equation comes out to be this neat. So if anybody doesn't have, does anyone have any questions about anything I did or about this equation in particular before I do some example? All right, so let's do an example. So let me write the equation again. And definitely know this equation. This is for charging a capacitor. The capacitor voltage at any time t, and I'm going to change that Vs out for a V in, because this is like the general form. 1 minus e to the minus t over tau. Do you guys remember when I said that tau was equal to RC? So that's the equation right there. Tau is my time constant. All right, so let's do an example. Let's say I've got a 12-volt battery, and I've got a switch. I've got a resistor of 1K, and let's say I've got a capacitor of 2 microfarads, okay? And I say that this switch closes at t equals 0. And I want to know, what is my capacitor voltage? Let's say at, I don't know, 4 milliseconds. What is the capacitor voltage after 4 milliseconds? Okay? Like, this is a potential question. So what I would do is I would say, okay, let's switch colors. I would say VC of 4 milliseconds is equal to, what's V in? Let's determine our time constant, tau. It's going to be R times C, right? That's it. So it's going to be 1 kilo ohm times 2 microfarads. K is 10 to the 3. Micro is 10 to the minus 6. So I'm going to have units here of 10 to the minus 3. 1 times 2 is 2. So my tau is going to be 2 milliseconds, okay? Everybody cool with that? All right. So now I plug 4 milliseconds in for t. All right, and now let me use my calculator to determine what that's going to be. So e to the minus, it's basically e to the minus 2. Does everybody see that? 4 milli over 2 milli gives me just 2. E to the minus 2. I'm going to 1 minus that, multiply by 12. I get 10, wow, sorry. Can anybody see this? Nope, you can't. Alright, just believe me, it's 10.375. Well, you're going to believe me when I do it in Spice, and it turns out to be exactly that. It's actually 10.376 volts. Okay? So that means that after 4 milliseconds, my capacitor has charged from 0 all the way up to 10.376. And remember, it won't charge up higher than this input, because what the circuit is trying to do is trying to reach steady state where the voltage input is equal to the voltage across the capacitor, because then it's in stability, right? It's not going to charge this capacitor to a higher value than this voltage, because the whole reason it starts charging is because current starts flowing until this voltage is equal, and then no more current can flow through the resistor, right? If this is 10.376, right, across the capacitor, and this is 12, there's still some little amount of current flowing through the resistor, which keeps charging the capacitor. But once this voltage is 12 and this is 12, no more current flows. Yeah?
So does that mean that T equal to infinity would go to 12 volts?
Exactly. Exactly. And so we usually estimate, I think last time I talked about this, after 5 time constants, so in this case it would be after 10 milliseconds, it'll be 99% of the way there. So it's exponential, like it goes to like 99%, and then it's just asymptotically reaching 12 volts forever. But if your time constant's 2 milliseconds, after a second it's going to be fully 12 volts. Like it's going to be fully charged. Obviously, it doesn't take an infinite amount of time to actually charge the capacitor in real life. It won't keep charging after some point. So you wouldn't sit there for infinity and waiting for it to fully charge. We typically just wait 5 time constants because it's 99% of the way there. And I can prove that, and I'll prove that later. Any other questions before I put this in Spice? Yeah.
Sorry, I'm still a little confused on how the capacitor would know, like, oh, I've reached that voltage.
It doesn't know, but
doesn't know.
it reaches that voltage and no more current can flow through the resistor just
Oh, okay.
because of Ohm's law.
So it's just like, basically it's like, okay, so it's just similar to like a voltage gate in a way, where like after it reaches a certain voltage, it kind of opens it. It's like no more current can flow through, but still allows the circuit to be closed in a way.
Well, more or less, the capacitor can't charge unless current's flowing.
Right.
And at first, right, you have no voltage here and you have 12 volts here. So you have a huge current flowing through this 1K resistor, 12 milliamps. But now that dVdt of that aspect of that equation, right, IC is equal to C dVdt. Well, I can rearrange that to say that dVdt is equal to IC over C. So the rate of change of my voltage is the current that's flowing into the capacitor divided by the capacitance, right? So as this, at first, this current is at a maximum, so my rate of change is at a maximum. That's why it shoots up really fast, like exponentially. But it turns into an exponential because the current is decreasing, so this dVdt decreases. And then once this current is 0, my change in voltage is 0. So mathematically, this voltage won't change anymore once it's 12 volts because the current is 0.
Right. Okay, that makes sense.
Does that make sense to everybody? All right, I'm going to go ahead and throw this in Spice, and then I'll do some more stuff. So this is going to be a 12 volt. You know what I'm going to do? Since I haven't introduced this to you guys yet, typically what I've been doing thus far is I've been using these switches, right? So I would close this switch at time t equals whatever. Instead, I'm going to make this a pulse source that starts at 0 and at some time it jumps to 12. Do you guys agree that that's the same thing as what's happening here? This node is initially disconnected, so it's at 0 volts, and then when I close the switch it jumps to 12, right? That's the same thing as a pulse source that starts at 0 and at some time jumps to 12, right? So you'll see both types of circuits. So what I'm going to do in Spice is I'm just going to do it with a pulse so that I don't have to deal with the switch. So my initial voltage is 0, my on voltage is 12. I'm going to delay it by 10 milliseconds. Somehow I put a giant Sharpie mark across my trackpad.
Magic eraser.
Does it work?
Don't take it off.
You don't think?
Be careful because it gets rid of lost edges, so if it's a matte finish, but just be gentle.
Okay, thanks. I'll try. Hopefully I don't get the electronics wet.
You can do it with rubbing alcohol. If you're worried about that.
Oh, alright. I'll just do that when I get upstairs then. Alright, so I'm just going to put 1. So, okay, so just in case I haven't talked about... Have I already talked about pulse sources?
Yeah.
Alright, so everyone knows what all this stuff does? All right. You know well enough. Well, it's good to know. It's good to know what they all do. All right, so what did I give this? I said 2 micro, and I said 1K. And then this is my VC, and this is my VN, okay? All right, so I'm going to run a transient. Okay, so a lot of people, how many of you guys are wondering how the heck do I know how long to run for? Have you guys figured out how I know how long I should run for? Okay, so basically, I'm turning this source on at 10 milliseconds, right? So I at least want to run for 10 milliseconds to see the source turn on. But then, I know that my time constant is 2 milliseconds. And I know that it should take about 5 time constants to turn on all the way. So that would give me 10 milliseconds plus my initial 10 milliseconds, or 20 milliseconds, and then I might just throw another 5 on there just so that we have a little bit more room. So I'll run for 25 milliseconds. So as you go through, these classes, you'll learn like how long is a good time to run for. It all depends on what you're trying to see. I want to see my signal turn on, and I want to see my capacitor charge, so I need at least this much time. And note that this time is telling me how much time I'm going to see in my sim. I'm not telling LT Spice to only run for 25 milliseconds. Like in real life, it's how long the simulation is going to show. Like if I put tran 25, it would show 25 seconds worth of crap, and all that I'm interested in is the first 25 milliseconds. So you're not going to see anything interesting. All right, so let me run this. So there's my input. This is a horrible color. Let's do red. So you see my input, it's at 0, and then at 10 milliseconds it jumps up to 12 volts, right? Well, my capacitor, as we mentioned, charges exponentially. Okay, and what did I say? I said after 4 milliseconds, so at basically t equals 14 milliseconds. That's what I'm curious about, right? I want to see what is the voltage at 14 milliseconds. So what you can do is you can click on the signal that you're interested in, and you get this little window right here, the cursor window. And it tells me the time that I'm at, and it also tells me the voltage that I'm at. I don't know if you can plug it. Yeah, I don't think you can type down here, which sucks. But what you can do, hold on. You only want one cursor for now. You can drag the cursor, and do you see how this, like as I go down, it's going down in time? And as I go up, it's going up in time and voltage. So I said 4 milliseconds, so that would be at 14 milliseconds because I jumped up at 10. And so right there at 14, it's 10.378, and I calculated 10.376. I'm off, guys. Sorry.
But you're also at 0.00545 milliseconds, so we'll give you that one.
I know. I'll give it to me too. You might be able to get closer if you drag this down more, because then you have like more voltage to play with. Yeah. If you really want to be like super fine about it, I could probably get to like. Oh, look at that! I'm still off. I got 3 sevens. All right, it doesn't matter. I got it. Does everybody see what's happening here? So note that I said time t equals 0, right? I said t equals 0. In this case, it jumped up at 10 milliseconds. So when I say, like, what is the voltage, where am I at? Oh, I'm going for the camera. What is the voltage at 4 milliseconds? What I should have, if I were to say that this closed at 10 milliseconds, like actually happened in the sim, I would ask what's the voltage at 14 milliseconds, right? I wouldn't ask what's the voltage at, if this closes at t equals 0, 4 milliseconds later, it's going to be 10.36. But in my sim, it closed at 10 milliseconds, so I look at 14 milliseconds. Does that make sense to everybody? So what I could do to change that is I could go... Why do I keep clicking on this? I'm closing this. It's driving me nuts. All right, so if I go back in here, I could make it to where my time delay here, I put 10 milli, I could put 0. And so it'll basically just jump to 12 immediately. And that's what I had on my paper. And then I could actually check 4 milliseconds instead of 14. You see that? It immediately jumps. But I don't think that that's good. I like to see, it's up to you guys, but...
So you could write it 4 milliseconds after the switch closes.
Yeah. Over here, if I were to do it over here, I would write VC equals... Or what is the voltage at VC of 14 milliseconds, right? But then I would have to change this t equals 0 to t equals 10 milliseconds. because all these things mean different things, right? This is telling me when the switch closes, yada, yada, yada. Okay? So I want to see if I can find this plot online. That's kind of interesting. Charging capacitor. There's like plots that you can see for the time constants. I want to see if I can find a good one. Here it is. No, that's not good. Ugh. These all suck. Oh, this one's okay. Alright, so let's see if we can get a good look at this. Alright, so basically this is the case in every RC circuit ever. Okay? After one time constant, it's 63% of the way to the final voltage. After two time constants, it's 86% of the way. After 3, it's 95%. After 4, it's 98%. And after 5, it's 99%. Okay? Yeah.
Is that the same percentages for a bell curve in statistics?
Maybe. I don't know. I didn't take statistics.
Okay. I'm just saying that's interesting.
Oh, you're talking about like the
The
normal?
bell curve in statistics, and then there's the normal, how many...
It might be. I wouldn't surprise me. It pops up everywhere, so it very well could be. But this is the same case as when it's discharging, okay? So if I were to say that it was initially 12 volts and then I closed the switch and drained the capacitor, this plot is showing me that the same thing happens. After one time constant, it's 63% discharged, right? And after two, it's 86% of the way, basically of the way to zero, of the way to being discharged. So in this case, I did 4 milliseconds, which was 2 time constants. So if I wanted to prove that that was, what did it say, 86%?
Yeah.
I could just go and see, okay, so what's 10.376 volts out of 12? It should be about 0.86, right? So let me throw that in my calculator and see what I get. 10 divided by 12, 0.8646. So if I multiply by 100%, that gives me 86.5%. Okay. Any questions about this example or anything I did in LT Spice? Nope. All right. That's good. All right. So what I'm typically going to ask is for you to plot the waveforms. I think on the next homework I asked for that. You guys are going to have fun with the next homework. I think it'll be fun. It actually requires some thought.
I don't have it to print in color.
Oh, yeah, you got to print in color. Or yeah, you can submit it electronically to Abe. I don't really care. It doesn't matter to me. Now that I'm not grading them, it definitely doesn't matter. As long as you do a good job. I personally like, the PDF submissions.
I like them because they don't use as much paper, but I don't have a scanner. So.
Oh, yeah, so you can't do the hand calcs.
Yeah.
Yeah, or you could type the equations in Word, which is an absolute nightmare.
Yeah, that didn't work out so well with your grader.
Oh, he didn't like that? Oh, yeah, he didn't like yours. Well, I meant like the nice, neat, like insert equation, all the neat, but it takes forever. It's too long. It's annoying.
You have to go in there and go character selector on the computer.
All right, so what was I just talking about?
Homework.
We're just wrap.
Everybody give us an answer to one more.
You said we're going to plot waveforms.
Yeah, we're going to work through somewhere.
Okay, so sketch the waveforms. That's what I was getting at. The fact that you're going to have to sketch the waveforms.
So we
Because,
can't submit this one electronically because it's by hand.
Did you draw it?
well, you can draw them by hand and then scan it.
Oh, okay.
But what I mean is to sketch them by hand and then check it in LT Spice. And it's very easy to sketch these by hand. And this is why. We can go back to my... Don't do that. I know most of you will. Because that's what I did. But the reason I did that is because Baker didn't explain how easy it was to plot these things by hand. If you find the 5 data points, right? 1 tau, 2 tau, 3 tau, 4 tau, 5 tau, you can just connect the dots. He just wanted us to eyeball it. I don't think that's a good idea. So in this case, if I found, VC of 2 milliseconds, VC of 4, VC of 6, VC of 8, and VC of 10, this would be very easy. How many of you guys have a TI-84? All right. Well, TI-84s are great because you can put the whole function in, and then you don't even have to think twice about it. 1 minus e to the minus x over. All right. So I threw that in there, and then let's go to table. And I need x equals 0.002, 0.004, 0.006, 0.008, and 0.010. All right, does you guys see these values? So I've got 7.58 volts, 10.376, 11.4, 11.8, and 11.9.
How do you do that?
Two decimals is fine, guys. Honestly, it doesn't. And then 11.92. All right, so those would be my 5 data points. I think I said something about this in the homework. I deleted it because I decided to just talk about you. Oh, no, I didn't. No, I didn't. I said the best way to sketch the output waveforms is to plot specific data points at multiples of the RC time constant after charging discharging begins, and then connect the dots to draw a waveform. Okay? So that's what I expect you guys to do on this homework. So if I go back here, what I can do now is, all right, let's just put 2 plots here. So let's put that at 12 volts, and let's put this at 12 volts. And then this is t equals 0. And then let's go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I guess I gotta do it again. So that's 2, 4, 6, 8, and 10, and you just write like T, and then let's say V in I do in blue, and let's say VC I do in red. Obviously, you would probably be doing this with a lot more space, but let's just go 2, 4, 6, 8, 10, 12. 2, 4, 6, 8, 10, 12. All right, so for V in, I know that at time t equals 0, it's basically jumping up to 12, right? And then that's just going to stay for the duration. And then for VC, I would go, I know it's 0 all the way up to here, and then at my first point, 2 milliseconds, that's going to be 7, so that's 2, 4, 6, 7, I'll be like right there. At 4, it's 10.38, it's like there. 6, it's a little higher. 8, it's a little higher. So it's something like this. It definitely messed up.
Hit the dot at 1.
And so you could, go ahead and write these voltages if you wanted. I think it'd be best, etc. Is it clear what's expected on the homework?
That's the same every time. So when we're sketching it, can we just draw that guy and then put a couple dots on there and call it good?
It's not the same. It depends on the input voltage.
No, you're saying the
I mean, like the
values that
curve.
figured out.
Oh, the curve is going to be the same every time, yeah.
So is that okay?
Yeah, that's fine.
Okay.
But this is only for this one particular case, because now, let's say I pulse this 12 volts back down to 0 over here somewhere, then this is going to start discharging,
Oh, okay.
right? So different things like that will start to happen. I think on this homework I gave 1 charging. This one is, so it's initial, if you see the initial condition is 0, that means it's charging, right? Because the capacitor is initially discharged.
Right.
If you see the initial condition where the voltage is some non-zero value, that means that the capacitor is discharging. Okay, so in this case, so there's a different equation, very slightly different, but almost the same.
The 1 minus.
It's just not the 1 minus. Yeah, did you guys learn this in physics already?
I did.
You did?
I don't know if I missed it.
Oh, okay. Well, yeah. In the case where we're discharging, it's the same exact equation. So let me write it down here real quick. I'm not going to derive it again. I don't think it's worth it.
You're not on the camera.
Oh, thanks. a capacitor. So in this case, VC of t is basically equal to my initial value that's stored on the capacitor, so I'll call it VCI. That's the voltage initially on the capacitor, times e to the minus t over tau. There's no 1 minus. And so you could also say that this Vin is not necessarily Vin, but rather it's the final value of the capacitor. Oops, I wrote that wrong. VCF. It's whatever, because it's the same thing, right? 12 volts is my source voltage, but it's also the final value of the capacitor. The capacitor is going to charge up to 12 volts. So you could replace VCF there, and then in this case it's VCI, right? This is the initial charge on the capacitor. This is the final charge on the capacitor. I'm saying charge, I mean voltage. And so let's do maybe one discharging example, since I've got about 9 minutes before I want to give the quiz. Any questions about anything I have on this page before I go to another page and do a quick discharging example? All right. Is this stuff making sense? That's good. All right, so let's do a quick discharging capacitor. Let's say I've got a capacitor sitting here, initially charged. I've got a switch. I've got a resistor to discharge through. We'll call this 10 microfarads, and let's go 5K here. And let's say that the switch closes at t equals 5. Hold on, let me figure out what the time constant is. 50 milliseconds. So let's just say that it closes at 50 milliseconds. All right. And let's say that my this is my VC, and my initial VC is 10 volts. So that means that my capacitor is starting at 10 volts, right? And obviously this this node is starting at 0 because it's connected to this resistor, right? It's shorted to ground through the resistor. So when I first close the switch, I'm going to get the capacitor to start discharging through this resistor, where this is initially, this voltage is basically going to jump up to 10 volts when I set the switch, because it's going to be connected to the capacitor. And now current will start pouring out of the capacitor. Basically, it's pulling charge off of the capacitor, and so the voltage is going to be dropping down to 0. And so that's what we'll see in SPICE. But let me do, like, let's say I asked, like, what is the cap voltage at t equals 150 milliseconds. All right, I could potentially ask something like that. And so in this case, you would say, oh, okay, well, I know my discharging equation, VC of t is equal to the initial cap voltage times e to the minus t over tau. And in this case, my tau is 5K times 10 microfarads, which gives me 50 milliseconds, right? And so VC of t equals VCI e to the minus t over 50 milliseconds. However, I did say that my switch closes at t equals 50 milliseconds, right? So if I wanted to write the correct form of this equation, I have to subtract out that 50 milliseconds up here. T minus 50 milliseconds over 50. Because now if I put in time t equals 50 milliseconds when the switch closes, right, I'm going to get 0 here, which is that's basically my time 0, because that's when the switch closes. And then when I put in 100 milliseconds, that's after one time constant. And when I put in 200 or 150, that's going to be after 2 time constants. So make sure that based on when the switch is closing, you're going to have to include this basically offset up for the time when the switch closes. So in this case, I wanted to know at 150, My VCI was 10 volts. E to the minus 150 milliseconds minus 50 over 50. And now I'll throw that in my calculator. Let's see. It's going to be E to the minus 2 again times 10. 1.353 volts. So it's discharged. Again, I did 2 time constants, so it's discharged 86%, right? So if I do 1.353 divided by 10, it should give me about, what the heck? Not divided by 10. Is that right? Oh, yeah. 1 minus 86%. Okay, yeah. You see that? 86%. All right, so let's throw it in Spice. I've got 4 minutes, and then I'm going to give you the quiz. So in this case, I'm going to have to draw a different circuit. I've got a cap. I'm going to need the switch in this case. And then I have my resistor out here. What in the world? 5K. Call this VC. Call this VR. Ground this. How do I set the initial capacitor voltage to 10 volts?
You have to do the text thing. Spice directive.
Good, right? Just like that. And then I need to do my switch model. Don't forget that. And now, lastly, I need a source for my switch to close at the time when I specified. I can ground this to the same one. And then I'm going to go with a pulse. I'll start at -1 so the switch is open, right? And then I'll pulse up to 1. And what did I say, 50 milliseconds? That's when I want it to close. We'll go with 1 pico, and we will keep it on for 1 second so that it just stays closed. Alright, and then I will run. So I'm going to run for the 50 millisecond delay and then 5 time constants plus a little bit. So that's going to be about 350 milliseconds. Dot tran 350, and let's run. So my cap is basically discharging starting at 50 milliseconds. And what did I want to know? I wanted to know the voltage after 2 time constants, which is at 150 milliseconds. So let's go look at it. So 150 is right there, and I've got 1.354, and I calculated 1.353. All right. Everybody good with these equations? All right, let me look at the homework and see if there's anything else that you might need from me before I send you off. Sketch the waveforms by hand, verify that they're correct. Yeah, this is the fun one. So it says repeat problem 1 for VI, VX, and VO. So basically this is charging and discharging capacitors using pulse sources. This is the same thing but using the switch. It's the same thing, right? The switch is going to close and then this capacitor is going to charge. All right. But then I asked, so what you'll notice is that in this circuit, when the switch is going to open back up, so it's basically open initially, right? And then the capacitor, it's going to close so that the capacitor charges and then it's going to open back up. And I ask you, in your own words, to describe the operation of the circuit. So what I'm expecting is for you to say what I just said, basically, but in detail. Like, initially the switch is closed, this is the state of the circuit. After the switch closes, this is what's taking place, right? Like, discuss what's happening in the same way that I would. You'll notice that like it's not as easy as you think it is to explain what's actually happening, even if you think you know what's happening. So try and explain it, write it out the best that you can, and then something interesting is going to happen here. The capacitor is not going to discharge when this switch opens. And so I want you to come up with a plan to discharge the capacitor and talk about why it doesn't discharge in this circuit when this switch opens. So some of you may already know or think you know, so that's that problem. But if you don't know, it's going to require some thought, and that's good. Any other questions before I give the quiz? Nothing? All right. Let's do it.